Hi everyone, this is just a quick video going through the remainder of the residual analysis that we started looking at in class Monday. So before we get into residual plots, just a quick little explanation here and using another little diagram just to show you what we're talking about. So what we looked at Monday was this idea of the residual value and how we actually calculate that distance. So if we're thinking about the actual data point and where it lines up vertically on the line as the predicted data point, that distance is giving us the residual value. If we were to calculate the residual values for every single data point on that plot, the next step is then to turn that into a residual plot, where our EV, our x-axis, will still remain as, in this case, this example, height. But then the y-axis, our RV, would be the residual value. The reason we do that is we're looking to check for linearity. So is our original data actually of linear form and not just tricking us by eye? So in a really super simple way, what a residual plot looks like, if I have an original scatter plot like this, and if I imagine that I can rotate my page, so I'm just going to do it really simply here. If I rotate my page so that I've now turned my graph and my equation, my line is now horizontal. This is a really basic view of what a residual plot would look like. Obviously the distances are slightly different because our residual values as such are actually vertical, so at a right angle there, but it does give you an idea of what points will be above the line, okay, and what ones would be below or close to, and how far away each of those values would be. So let's have a look now at what we're looking for in a residual plot and then also how to construct one. Okay, so as I've said, a residual plot is graphing the residual values against your original EV or X values. We plot this to help us work out the linearity. And so if we do have linear data, we need two things to exist. We need our residual plot to be approximately evenly split above and below the x-axis. And what that means is that the points, the data, should be roughly half above and half below. We say roughly because you're rarely going to get an exact split, 5 dots above, 5 dots below. You might get 4 and 6. Okay, in a big data set, there might be a few points difference above and below, but it's just a guide, so approximately evenly split. And importantly, you also need your residual plot to be random, no clear pattern, just a bunch of dots. So whereas previously with the original data, you want to see that form, that linear pattern, that straight line pattern. If your data is in fact linear, your residual plot should have no pattern at all, should be nice and scattered. And so we have an example here of what a no pattern linear relationship looks like as a residual plot. You might be able to see there, it's a bit difficult to see, that we've got residual as our response variable, our y-axis there. And so you can see we've got 1, 2, 3, 4, 5 points below the line, 1, 2, 3, 4, 5 points above the line, and there's no discernible pattern. So we are happy to say that it meets both of the criteria and our original data is linear. Okay, so importantly, I'm saying my original data is linear. The second scenario, when our data is non-linear, we either have uneven split or our residual plot forms a pattern. So there's an example of that here. This is a really obvious pattern. It's got that U shape. Okay, we also don't necessarily have an even split of values, but I look at that and I can straight away see there is a pattern there. The data is starting above the residual line, dropping below in the middle, coming back up again. So there is a pattern. Okay, I can draw a line through that pattern and follow it. So that means my original data would have been non-linear. Okay, you can see here we talk about, and therefore a transformation is required. So at the moment we are fitting linear models, regression lines, to linear data. But if we identify that our data is non-linear, we don't just stop. And in the next section, we will look at how we can go about transforming data and making it more linear so the model is appropriate. But for now, we're just concentrating on how we identify whether they're linear or non-linear. Okay, so looking through a few examples just to quickly see what it is we need to do. This first example here, this is our residual plot. We've got heaps of data points. Now, I'm not going to count them all individually, but I can gauge by just looking at it, there seems to be a relatively even split. Roughly half the points above this residual line, so the 0 line is what I mean by the residual line, okay? Roughly half the points above, roughly half the points below. So we have tick, an even split. Second thing we're looking for is there a pattern? And so I can say no pattern, that appears random. So tick, random. Remember, we need both of those things to be able to say my original data was likely to be linear. Let's look at this second one. So here, without even thinking about it, I can see that we have this U shape happening again, starting below, going above the line, and then back below. So again, when I say above and below the line, I'm talking about the 0 line here, which is my residual, I guess my linear equation on the original graph is represented by that 0 line. And so here we can see there is a pattern. Okay, we have a curved shape. And we may need to say that when justifying, and so therefore our data is non-linear. Our original data would have been non-linear. Final one, again, here I can see pretty clearly there is that sort of curved shape to my data. If I wanted to check the points, I've got 1, 2, 3 above that 0 line. Okay, there's the 0 line again, and 1, 2, 3, 4, 5, 6 below, so it's uneven. Okay, so uneven split and pattern or curved shape. And so therefore my original data would be non-linear. Okay, on page 37 of your notes, we have this example here, and above that gives you some pointers about how to construct a residual plot in your calculator. So I'm going to use this example and this data to find the residual values it's asking for, and also show you how to construct a residual plot for that data. So here in a lists and spreadsheets page, I've entered in those 2 sets of data. So remember, whatever you call your columns, that's up to you. Use at least 2 letters so it's less confusing. I've just called them hours and fish for fish caught and hours spent fishing. Now, in order to have a look at a residual plot, we first need a scatter plot and we need a regression line. So I've gone ahead and already done that. So there's my scatter plot with hours as my EV and fish as my RV, and I've calculated the regression equation there. I'm just going to pop that out of the way a little bit because we don't need it. So in order to see what the residual plot looks like, remember it's going to be roughly like if you turn your head to the side or you rotate your calculator around so that the regression line becomes that 0 line horizontal. But in order to show that plot, if we go into our menu and we go into Analyze and number 7, Residuals. And so here we want to show the residual plot. What that will do, keeps your original scatter plot above, and then underneath it gives you that residual plot. So again, if I just move that equation out of the way, and so we can see here that first point at 1 is now at negative 0.66. So that point there, what that means is this directly corresponding value here for 1 hour is 0.66 units of fish below the regression line there. Okay, so it's just a little bit below. You can see the second data point at 1.4 hours is a little bit further below, and that's represented here in the residual plot. It drops down a little bit more. Okay, and the residual value is actually negative 0.152. So something you can do if you have to fill out that table of residuals is actually hover over and read off those residual values. The problem with that technique is that if the calculator is giving that at this point correct to 2 decimal places, but you might need a different level of accuracy compared to what this graph will show you. So just be aware that it can be useful, but it might not give you the full amount of information you need. So a different way of getting those residual values, if we go back to our lists and spreadsheets, once I have calculated a regression line in the lists and spreadsheets page, so in this page instead of straight onto the graph, what I am able to do is get the calculator to show me the full list of residuals. This is similar to what you have in your notes just above the example, but I do it in a slightly different way. So I'll show you my technique and you choose what works best for you. So firstly, we need our regression equation. So again, stats, stat calculations, and number 4, linear regressions. Our X list, we said, was hours. Our Y list is fish. Hit OK. Now, in the calculator notes, it says if you arrow down until you see the word resid, it then brings up, if I hover on that cell, all of those numbers for you in a list. But that's hard to read and keep track of. They also come up down the bottom in the grey box at the bottom. But again, it's showing you, particularly if you've got lots of data, more than the 10 points that we've got here, it can get a bit tricky to keep track of. So the way I do it, if I go back to any empty column and I click in that middle grey cell, so where you put the formulas, what I'm going to do now on your calculator, the button VAR that is above, and if I just include that here, so a quick view for you here, I'm talking about the VAR button here above the number 9. Okay, so when I click that, if I go down to number 3, link to, you'll see that it brings up a lot of options, a lot of stat things. So I want to pick up the one that says resid. Now at the moment mine says stat1.resid. If you have done multiple linear regression lines, it might say stat2, stat3, stat4, stat7, stat21. Please, when you start a new exercise, a new class, start a new document, and then you'll always have just the most recent information in there. But for now, pick your stat resid, and you'll see now it's populated this column. Okay, so it's given you all the way from the top, scrolling down, all of those residual values, and you can see which ones they match up against. Okay, so at 1.4 hours, the residual value there is negative 1.52. So now you can go back to the table in the example and we can fill out those residual values just from the answers here. Okay, and as you can see, I've now filled in that table of residual values. So this is something, if you have the raw data and you're asked for one single residual value, you can use this technique rather than the predicted values and actual values that we looked at last lesson. But it's not often you get all of the original data, or it's time effective to put it all in your calculator to get these values. So it just depends on what the question is asking you. Okay, having a super quick look at some of these VCART questions now, starting on page 38. So here, 2013, paper 1, question 11, we're given the scatter plot with the regression equation plotted onto that, and we are asked to match which of the 5 options below is most likely our residual plot. Okay, so which one is the residual plot? Remember, if you pick up your piece of paper, rotate it slightly, sort of that way, make the regression equation horizontal, so that's a 0 line, and checking what you can match. So the first thing I would notice is that these first 2 points are below the regression line, which means in my residual plot, where I've got my 0 line, I would expect the first 2 points to be below the line. And then the 3rd, 4th, 5th, 6th, and 7th all to be above the line before the final 3 drop down below again. So I would be expecting sort of that curve, but what I'm going to mainly look for, where the 0 line is and are the first 2 points below the 0 line. So if I look at the options here, A, the first 2 points, so it's a little bit difficult to see where your 0 line is, so it might be worth highlighting it so that you can see that nice and clearly on the options. My first 2 points, yes, are below, so at the moment A could be an option. Okay, B, first 2 points are below. C, first 2 points are below. D, no, they're above. So I can knock out D, and we'll just move down slightly. And E, first 2 points are below. I'm then expecting the next 7 points to be above the line. So A, I would say, is still an option. B, we've got this random one in the middle here that's dropped down. So no. C, still kind of an option. D, we've already knocked out. E, we've got this one that drops below here. So no, we can knock that out. Finally, we said the last 3 points should be below the line. So of our options we've got left, A and C, 1, 2, 3. Here we've got on the line, just about on the line, and 1 below. So what's the difference there? I want to see this point, yeah, that's very close to, so it has a really small residual, so it'll be close to the 0 line. But this second point at 8, so again, it's in line with 8 on the x-axis. This one's in line with 8 and is a bit further down. This one is not in line with 8 and is a bit too close. So I'd say no, A is my best answer there. Okay, the second VCAR question here from the 2016 paper 2. We were given a residual plot after the least squares regression line was fitted to the data, and that's shown below. The residual plot can be used to test an assumption about the nature of the association between two numerical variables. What is this assumption? So why are we doing a residual plot? Because we are testing that the original data is of linear form. So that's our assumption. Then in part 2, they are asking, does the residual plot support this assumption? And so if we're looking here at this residual plot, we're looking for how many points above and below the line. And so I've just highlighted the 0 line to make it a bit easier to see. We've got 1, 2, 3, 4, 5, 6, 7, 8 points above, 1, 2, 3, 4, 5 points below. So it's not exactly even. Some of those are quite close. There's not a big clump of data above or below. And the second thing is it randomly scattered? So I don't think we've got a clear pattern. We're sort of going up and down as we move across, and there's no clear pattern there. So I've said, yes, the residual plot shows the values are approximately evenly split above and below the x-axis and are randomly scattered. So now we come to the point where we're putting it all together. As we've been saying as we're going along, we are talking about everything we've done from the point where we start with numerical bivariate data to 2 sets of numerical variables. And so here, I'm just going to talk you through really quickly how it all fits together, and then I'll have this filled out in the OneNote for you. So here we have the hours of sleep and the number of rapid eye movement occurrences of 10 adults being recorded. And so you can see there in the table, we've got the hours of sleep and the REM occurrences. In this investigation, which would be the response variable? So first thing, way back at the start, RV and EV, and which would be the explanatory. So being able to identify that our hours of sleep would be our explanatory variable, and that would help explain the change in the REM occurrences. So REM would be our response. Part B is asking us to draw a scatter plot for that. So if this was a SAC, you might be asked to draw a scatter plot. You may be given a grid with axes marked on it, but if not, definitely constructing your own scatter plot, knowing how to do that. And then using your scatter plot for part C to comment on the relationship. And now we're talking about describing that scatter plot in terms of direction, strength, form, and outliers. Once we've done that, we're then asked to calculate a couple of statistics. So finding our correlation coefficient, or Pearson's R, and interpreting that value. Remember, Pearson's R gives us strength and direction. So confirmation of those 2 things out of the 4 that we've described in part C. Part E is then asking us for the coefficient of determination, or the R-squared value, and asking us to interpret that. So talking about the percentage of variation in the RV that is explained by the percentage variation in the EV. Moving on to part F, we're then asked to calculate our least squares regression line, state our answer in terms of the variables, so in the context of the question. Moving on from that, where we interpret our slope and our y-intercept, so giving meaning to that slope, what's happening, what units of change are happening for every 1 additional hour of sleep, and our y-intercept, on average, when our hours of sleep are 0, how many REM occurrences are there, and stating whether that is a valid statistic or not, depending on the value. Then looking at part H, we're asked to do some predictions. So using the equation, when someone has slept 1.75 hours or 8 hours, and comment on the reliability. So here we're talking about our extrapolation outside of the given data range, or interpolation inside the given data range. Extrapolation, less reliable. Interpolation, more reliable. Part I is then asking us to construct a residual plot. So taking those residual values and comment on that, the appropriateness. So do we see a pattern? Is it evenly split? So does that mean my original data was linear or non-linear? And then finally, from your analysis, it can be said that an increase in number of hours sleep will cause an increase in the number of REM occurrences. Look for that keyword and tell me whether you believe that that is correct. Okay, so as I said, I'm going to go back and fill in this example for you so you have it. What you should be working on today is the exercises, or the questions, sorry, from exercise 3C, and a reminder that you can see all of what we should be doing this week in that little week 4 planner there. So 3C is what we're doing. We've tipped that over into our second lesson due to today's shortened lesson, or Monday's shortened lesson. Okay, team, I will see you again on Wednesday. Good luck with this. Come to class with questions.